Okay, today we're going to talk about the Hill equation, and then we're going to talk about a measure of how cooperative a binding is. So, the Hill equation is a simple sort of empirical equation for cooperative binding based off the Langmuir model. So if we remember the Langmuir model, we have our fraction of open channels, our K L over 1 plus KL. And this is for a ligand plus receptor goes to a receptor-ligand complex. So what the Hill model does is we mark that as KH to stand for K Hill. We raise the ligand concentration to what's called the Hill coefficient. And we can see that if H equals 1, then we just get the Langmuir model. And if H is greater than 1, then we have positive cooperativity. And if H is less than 1, we have negative cooperativity. And if we were to make a plot of this, if this is our Langmuir model, H equals 1. If H is less than 1, we get something that looks like that, a little sharper increase. And then if H is greater than 1, we get something that looks like that, where there's a little bit of an induction period. So we can kind of see that at low concentrations, right, it's hard to bind. And then once we start binding, actually this will probably come up, it's probably surpass this. Once we start binding, then more and more, or it's easier to bind. So over a smaller range of concentration, we get a large rate rise in the fraction of binding channels. Okay, so this is the Hill equation. Let's solve the half bound case, just like we did for the Langmuir model. So we want y equals 1/2. So that's going to be KHL. Call that L 1/2 over 1 plus KH L 1/2 raised to the H. All right, we just bring this across. So I'll bring this 2 across, bring the denominator across. Now I can bring this over to this side by subtracting. So I get 1 equals KH L 1/2 to the H. So L 1/2 to the H, or L 1/2, is 1 over KH to the 1 over H. It's the 8th H root of the equilibrium constant. Now, H could be an integer, it doesn't need to be, it's just some variable parameter for the Hill model, but certainly could be an integer. All right, well, how do we determine how cooperative something is? Well, there is a condition for that. And if we define Q to be Y times L of 1 minus Y. We'll just make this definition. And then if we take the derivative of Q with respect to L, if this is greater than 0, then it's positive. And if it's less than 0, then it's negative. All right, well, let's just do this for the Langmuir model first. And we know that that is neither positive nor negative, so we should get 0. So let's go ahead and plug this in. So for the Langmuir model, Q is KL over 1 plus KL over L times KL, or 1 minus KL over 1 plus KL. Let's get this over the common denominator. Now we get some cancellation. These terms cancel here, and these denominators cancel. So we get KL over L. So Q equals K. So dQ dL indeed equals 0 for the Langmuir model. So it's neither cooperative, positively cooperative or negatively cooperative. It's just neutral. All right, well, let's do it for the Hill model. And actually, I'm gonna just, well, you might be writing notes, so I'll rewrite this. Let's get a common denominator again. And just like with the Langmuir model, we see some good cancellation. These terms cancel, the denominators cancel. So I'm left with K L to the H over L. So Q is K L to the H minus 1. So I can take my derivative. And we see that this whatever this is positive. And so here, if H is greater than 1, then this whole thing is positive, and we get a positive cooperativity. And if H is less than 1, right, then this is going to be negative. So we get a negative, which is a negative cooperativity. Just like we said for the Hill model. All right, let's try a little bit more complicated. So let's do the Adair model. We're not going to do the one that was in the previous video. That's going to be a little bit too messy to really be worthwhile. But let's use the two-state model, and I'm just going to tell you what that is. We won't go through that. I'll tell you what Y is for that. So for the two-state Adair model, so there's my Y. So let me write my Q. There's Y over L times 1 minus Y So let's get this over a common denominator. There's my numerator. I have L times 1 plus 2 K1L, K1 K2 L squared, minus all of this, well, we get some good cancellation again. So we get that. So dq So we get, I think I have an error here. Let's find it. Oh, yes. I was too quick to cancel. So this is a 2K. And so I can cancel one of those. And I can cancel the denominator. So let's write that out. Yeah, I think this is it now. Right. Okay, so here's Q. And dQ dL is K1, K2 minus K2, K1 squared. Over 1 plus K1L squared. So you got to use a quotient rule and chain rule and stuff. But this gets us here. Now, this is always positive, right? So this is proportional to K1, K2 minus K1 squared. And so this is what we were saying about the Adair model. If you go back and watch that video, if we have a sequence of Ks, if the Ks keep getting bigger, we have positive cooperativity. If the Ks keep getting smaller, we have negative cooperativity. Well, here we see it for the case of 2. If K1 is greater than K2, right, then this is going to be negative. And if K1 is less than K2, this is going to be positive. So negative will mean negative cooperativity. Positive derivative will be positive cooperativity. And finally, if K1 equals K2, then we get the Langmuir model because it's going to be equal to 0. So this actually holds true even for a 3, 4, 5, 6 state model for the Adair model. If all the Ks are equal, then it just reduces. It will automatically reduce down to the Langmuir model.